Welcome everyone to another OCP Tap call. This is call number 128. We have Rodney today that's going to give us an intro about 1588 and the latest updates. So as usual, we'll start with the bio. Rodney has 35 years experience working for National Instruments and Keysight, and has launched products families for testing of network protocols. These testing products have addressed at industry and application, industries and applications for, again, related to timing and synchronization and determinism and management and anything related to these topics. He is currently the vice chair of IEEE 1588 working group, and he worked also on various standards such as the IEEE 802.1, IETF, ITUT, and ORAN, and has been basically working with Keysight as a timing architect on products for testing of time synchronization performance. He received his bachelor degree in computer science from the University of Texas in Austin in 1990. So with no further ado, Rodney, the floor is yours.
All right, thanks, Ahmad. So yeah, like I said, to give you folks a little bit of an intro to this slide deck. So we had a couple of cancellations, and so Ahmad and Hesham kind of asked me to kind of step in and do this slide deck. What this slide deck basically is, Doug Arnold, the chair of the 1588 group, and I tend to kind of do sort of updates on what's going on in the working group. There's usually a lot of stuff kind of going on, so it changes month to month. So we tend to kind of keep a slide deck to kind of as needed. Whenever anyone is interested, we'll kind of do an update on the standard and what's going on and things like that. So seemed like that might be an interesting topic for this group. And so that's what this slide deck is. This is not an official slide deck of the working group. You can kind of view it as just Rodney's opinion, at least officially, but it is kind of reflecting, what's going on and so on. Now let's see, there we go. So yeah, the agenda of what I'm going to go through is kind of introducing 1588 just in general, to kind of start with, what is the standard, what it's used for, and so on. Go through some of the things that have been published, amendments that have been published since the 2019 edition of the standard. And I'll describe what I mean by amendment as I go along. And then some projects that are in work, basically kind of going on now. And then potential things in the future that haven't started yet, but might. And I'll just kind of organize things like that. So what is IEEE 1588, otherwise known as the Precision Time Protocol? It precisely synchronizes time among devices in a local network, is sort of the brief way of describing it. That local network can be running Ethernet. That's one of the most common things, but it can also be OTN, a telecom technology, Wi-Fi, and there's integration with 5G. So it's not necessarily only Ethernet. It can be other media and other mechanisms. And the precision part of it kind of comes from the fact that there is almost always a hardware timestamp that is implemented in the hardware on both sides to precisely timestamp the messages as they leave the port and arrive and are received by the port. And that's where the kind of the precision comes from and the improvement compared to protocols like, say, NTP that run over the internet. So like I mentioned, 1588 2019 is the latest revision of the official standard. Relative to the previous one that most folks know for a long time, the 2008 edition, it is backward compatible. It has a minor version, so 2008 was 2.0, this newer one is 2.1. Lots of new optional features, lots of architectural clarifications, I would say. In general, in the time span between 2008 and 2019, you could kind of argue that PTP grew up, meaning what I mean by that is that it was used by very large networks with lots and lots of nodes and basically became very pervasive in actual installations, which then caused a lot of misunderstandings and clarifications and new things that people needed. So that's what kind of drove that 2019 edition of the standard. Another thing that sometimes comes up, the 802.3 standard, the actual standard for Ethernet, has a clause 90. I don't remember the title. It's something like timing something in clause 90. Some folks ask me, like, is that a competitor to 1580? I mean, to 1588? What's the relationship? I would kind of characterize the information in that clause as implementation help for 1588 for Ethernet. So basically, if you have an Ethernet PHY and you're implementing PTP, you would go there, and it would give you, in addition to what's in 1588, which, like I said, is kind of agnostic of what kind of layer 1 PHY it's working with. That gets down into more details of when you are actually working with an Ethernet PHY, what would you do for this timestamping? So it's very much a sister standard to 1588. It's not competing or anything like that, or really not even overlapping. It's really just kind of describing the implementation of a PHY, for Ethernet. Have a little diagram here kind of showing the basics of how it works. Essentially, you can think of this diagram as going over, say, an Ethernet cable, either copper or fiber. You send a message from one side. Precisely when you transmit that message, you timestamp it. That's this T1. That's received by the other side of the cable. You could think of it. That's timestamped precisely when it's received. That's T2. Then ultimately, the bottom line is you send another message in the other direction, and that's T3 and T4, basically taking the same measurement, just in the other direction. And when the side that's receiving time, known as the slave often, basically gets all four of those timestamps, T1 through T4, it can, assuming the cable is symmetric, which I'll get to a little bit later, isn't always perfect, but assuming the cable is symmetric, you can calculate the offset in time between those two and basically get the clock to match on both sides within some degree of error. And that's the basics of how the whole thing kind of works. So applications using PTP, basically nowadays, pretty much anything that uses a wired network, at least, that general industry will tend to use PTP these days. And that includes inside a car, inside a plane, inside a rocket, in a telecom network that's, say, connecting fiber to your home to bring you internet, inside a TV studio, a factory, you name it. There are millions of deployed products out there now that have PTP running in them. Actually, if it's okay, I mean, before I get into the stuff with the standard, it might be helpful for me to kind of switch over to that tutorial that I linked in the previous slide and kind of go over. Ahmad, tell me if you can't see this. So if you go to the public website for 1588 and you go to learn, well, and I have a link in the slides too, you'll find this little article that I wrote back in 2020. And I thought it might be useful to kind of go through that. So it kind of steps through the technical overview of, like, how does all this work? But then it goes down into some applications. And actually, I kind of figured I would use this to discuss the applications, just to kind of give some broad strokes, meaning very high level, very simplistic overview of how the different applications that use PTP use it. Meaning, in other words, like, why do they want to synchronize time, and to what end? And, so in other words, not quite getting yet into all of the details of, like, the PTP mechanics, but really more, why are they doing it? So I figured I'd kind of go through this just as a quick overview. So one example is CERN and White Rabbit, which is basically their profile of 1588. Fundamentally, what the basic research folks are doing, basically really big experiments, in this case, particle accelerators. Fundamentally, the reason why they need to synchronize time is, as many of us know, they have a big ring. It's not only the Large Hadron Collider, there's a bunch of different particle accelerators at CERN and at similar labs and so on, where you have a ring and you're shooting particles, subatomic particles, around this ring. And at some point, you need to track those particles. You need to know where they are. And at some point, you are going to collide them, and you need to measure the collision. So fundamentally, as these things are traveling around the ring, you need to know where they are. You need to know where they collide. You need to control them and so on. And that actually drives pretty tight synchronization requirements for all of the equipment that is around that ring. And this application in particular needs better than a nanosecond, essentially, in terms of like the worst case error between two clocks along that ring needs to be at a minimum within hundreds of picoseconds. Because of that, the PTP that this industry uses is the best, I guess you could say, in terms of performance. And again, that's not just because they arbitrarily wanted to have the best, it's because they require the best, because these particles are traveling around, and it's better than anything else that people are using PTP for. So I thought that would be kind of worth mentioning. Another really big kind of high volume network for PTP is telecom. So maybe one example I could use for that is, let's say that I have fiber coming into my house, and I've got 500 megabits that I pay for that fiber. And maybe my neighbor uses the same telecom provider I do, but they have a gigabit of bandwidth running to their house, and so on. So those links go out to the switches in my neighborhood, out through other switches, and then eventually to the internet. And the question becomes, let's say we have the same provider, just to keep it simple. How does the telecom provider make sure that my neighbor gets 1 gigabit, no more? I get 500 megabits, no more. So I get half. The general practice for a long, long, long time in telecom, even before Ethernet, was that use a time domain multiplexing technique. You have time slots, and you're basically allocating different people's packets into time slots. And I won't go into all the boring details on it, but ultimately you're using clocks as this traffic travels upstream into the internet and so on. And you're using that to kind of manage your time of different clients and different customers and so on and so forth. And so the performance of those clocks is very important, especially as you get into higher speeds. So the telecom industry has fairly tight requirements. Nowadays, it's in, I would say, the low nanoseconds. So not quite as stringent as, say, CERN's, but still pretty stringent. And there's millions of this stuff out there running PTP. Basically, they need to run something to synchronize all their clocks in their network for the purposes of traffic management, is sort of the easy way to say it. Another example, so in this paper, I kind of lumped industrial automation and automotive. You could actually lump aerospace, like inside a car. It's very similar. I'm kind of oversimplifying it, but what you could think of as, you have multiple boxes on a factory floor or inside a car. Each one of these boxes is doing something like, say, every 10 milliseconds, read your inputs, do some compute, send your outputs. Like in the case of a car, it might be, I detect that my wheels are slipping due to somebody applying the brakes. I need to do anti-lock brake system as an output, so let me do that. In the case of a factory, maybe you're watching, I gave an example of a bottle going past, and you want to fill the bottle. You've got something that's watching that and has to fill it, and so on. And the key thing that they're using PTP for is, you've got a network of some sort on a factory floor, in a car, in a rocket, whatever it may be. And each one of these things is running its own compute cycle. Well, it makes sense that you would want to synchronize all these. So say if each one of these is running 10 millisecond cycle, it'd be nice if they were all running the same 10 millisecond cycle, exchanging data at the same time, because that makes the whole system a lot more reproducible, a lot predictable, testable, so on and so forth. And they will often use PTP for that purpose. As you might guess, like say within a car, it might be like 1 microsecond. So it's not nearly as aggressive as even the telecom use case. In the case of a factory, you might have 100 of these things, and they get to more rigorous requirements for the simple matter that they have a lot more stuff to synchronize, but it's still fundamentally the same sort of thing. Television broadcast studios. So you've got audio and video. The audio and video are traveling in different packets through the network, but yet to the end customer that's watching a show or a movie, that audio and video has to be synchronized and has to be the same. That's one of the reasons that they synchronize things, is basically to get their audio and video all lined up. and also to switch from, say, one anchor to another anchor seamlessly without making things kind of look stuttering or staggering or anything. And that's why they use time sync. Electrical distribution, this one's also kind of obvious. You've got power going through these lines running at, say, 50 hertz or 60 hertz. You know, we all know generally how fast AC waves tend to cycle. You want to detect faults along this entire distribution channel, and they use these things called synchrophasers to basically do precise measurements of that, say, 60 hertz waveform that's going through. One of the techniques is to use GPS, say, in the US at different sites to do this. More and more now, they're starting to use PTP, and they have profiles to do that. So essentially, they're just trying to measure the AC waveform as accurately as they can in as many different locations as they can so that they can accurately detect when there's a fault, like a line getting knocked down and things like that. Financial networks, you've got packets that are many packets that are used to execute a trade in order to kind of make sure that everything happened at each step correctly. And mostly one of the issues is government regulators want to make sure that every packet at every step happened correctly at the right time. And so there are actually regulations in this industry to mandate that timestamping is done at various points, and PTP is useful for that purpose. And again, the performance requirement in a way is kind of set by the governments. So anyway, I just wanted to kind of like briefly go through that to kind of just give folks a sense of like what the requirements are. Now, I think I accidentally closed PowerPoint. Let me launch that again. So with that, I can kind of go through the actual standard committee. Let me swap that again. Let me know if this isn't appearing correctly. So yeah, that's kind of the applications. Each one of these industries has a profile. You could think of a profile as this is the way that I'm using PTP. These are the options and so on. So for example, in industrial automation, there's an 802.1as standard that builds on top of 1588. And then there's an industrial automation specific standard that sets firm requirements for performance and so on and so forth. 5G front haul has a similar specification that builds on some of the telecom profile stuff. That's a common thing that happens. So I'll get into amendments. So this is basically projects that have happened since 2019. The first one, this is one that I'm talking about that was published 2023, so a couple of years ago. Basically, what this amendment did was for multicast, PTP has an algorithm that finds the best grandmaster, basically finds the best clock in the system and then routes paths from that clock to all the other clocks. That best grandmaster might change, like if it fails, it'll switch over to a backup and so on and so forth. But generally, the paths were kind of determined by hop count. So in other words, basically just kind of counting switches dumbly through the network and saying, okay, this is one hop, this is a second hop, and so on. Well, it's hypothetically possible that you might have a path that has more switches in the path. It's kind of shown in green here. But even though there's more switches, 3 instead of 2, that one implements PTP better and has much higher precision. Therefore, you want to go through that path that has the 3 switches in it. There is a, in the 2019 standard, there was a type length value, basically a blob of data that could propagate accuracy information through the network. What this amendment does is basically integrate that information into the algorithm that decides the grandmaster, so that as an option, you can basically pick that nicer green path that had 3 switches instead of 2. And for now, the main industry that's actually focusing on using this is the telecom industry in ITU, or considering using this amendment. And like I said, this is a published document from IEEE. This one, 1588E, is one that I worked on. This is kind of also part of PTP kind of growing up. you need to be able to manage the PTP that's inside, say, a switch or a router. And MIB and YANG, I won't go into all the details, but they're basically standards for doing that, for basically kind of remotely running a client that can talk to the switch or router and then configure everything about PTP that's in it. The YANG that was published by this amendment is already being used by IEEE and ITU and ORAN. So you can basically build on it to do complex network management tasks. I kind of lumped 4 other ones in one big slide. These are all published again. Mapping to optical transport network, OTN is a networking technology used in telecom, more for kind of core upstream applications, and it uses PTP for much the same reasons that I described. And this basically just kind of says, you know, where is the timestamping point in the OTN frame, things like that. Basically, how do you map it precisely to a particular point at the layer 1 level? 1588G, that was a optional alternative terminology for master slave. So basically, the 1588 standard didn't change terms, but if another standard wanted to use something other than master slave, it specified time transmitter, time receiver, and ITU and 802.1 use that. 1588D, guidelines for GDOI security. So there's 3 basic ways to secure PTP. One is physical. By that, I mean, I've got a room, I've got guards, I've got doors. I'm happy with that. You know, not everybody is, but some applications are. MACsec, which is basically a layer 2, you know, hardware level security. You can secure PTP frames that way. Not everyone likes MACsec. So another way is 1588 specifies an authentication TLV, which is basically a 1588 specific way of securing the protocol. But that 1588 feature requires a key management protocol, basically something to kind of exchange the keys throughout the network. And 1588 does not define that. But in this case, there is an IETF standard that defines a key management protocol called GDOI. IEC for power distribution, the application I mentioned earlier, wanted to use GDOI. And so this Amendment D basically pulls all that together, pulls stuff from IEC, pulls stuff from IETF, and puts it all in the 1588 document and describes how to use GDOI. And then 1588C was various clarifications I won't go into. They weren't too major. So to give you kind of a sense of these amendments, oh, actually, I think I have it in the next slide. So yeah, so now I'm going to talk about things that are in work now. So these are not published yet, but they're being worked on in the group. So one really big one is the roll-up revision. And so what those previous amendments that I talked about earlier, if you get one of those from IEEE and you read it, it'll read as an amendment, meaning, in other words, you'll see it almost like a track changes device. It'll say things like, insert this paragraph, or, you know, insert this new word and strike out this other word. And it reads like that. So it's difficult to read, obviously. And if you have multiple of these amendments that have piled up, let's say you have 2 amendments that change the same paragraph of text. Well, that's really hard to make sense of, right? Because now I've got 2 documents and they both change the same thing. So IEEE's practice is, you know, hey, it's okay to get these amendments out as kind of a quick thing to get the industries going. But at some point, you need to do a complete revision of the document that is clean, meaning it has all these amended changes in it, but it's just a normal document, no underlines, no strikeouts, no anything like that. It's just the document. So in larger IEEE groups, the way this is typically done is with what's called a roll-up revision. So what a roll-up revision means is literally it's only editorial. All the editor is going to do is pull in all those past amendments that have been published, pull them into the document, and basically remove the underlines and the strikeouts, but make the change, and then publish that as a document. So in other words, there's no technical features well, there are technical features from the amendments, but The roll-up itself has no technical features. It's really just pulling in those things and then publishing a document that's clean. So that's in progress. We have our editor for 1588 is working on this now. And more than likely for it to just go through all the balloting and other stuff like that, it might publish in 2025, but more likely it'll probably be sometime early next year that it'll be published. So everyone will see that as 1588 2026. So now the question will become, wow, that's a new version of the standard. Is that the same version? You know, is it different? What changed? Recently, in one of the meetings in 1588, we went through and asked ourselves all of those amendments that I just discussed. Did any of those change the way things work in the messages, or semantically? Like, did it change any of the state machines or the way the protocol works? And the answer for all of those amendments was no, 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 no. So when this document is published, the consensus so far is that it's going to remain version 2.1. So it won't even be characterized as a new version of the protocol, even a new minor version. It'll just be the same protocol, but publishing all these amendments in a new version. And for those of you that are familiar with 802.3 Ethernet and 802.11 Wi-Fi, that's the way they work too. So we're basically going to try to transition into a model where we publish new features in new editions of the standard, but we're not asking people to go write a bunch of new code for this. It's all compatible, it's all the same. And that's kind of the idea there. So one of the amendments we started in around 2020, 2021, that's not quite done. A lot of work has been done in it, but it's probably not going to make it into the roll-up, is 1588F, latency and asymmetry calibration. So I tried to kind of capture this in one slide, but the bottom, for applications that want to synchronize better than a nanosecond, which, as I said before, is mostly the basic research community, CERN and so on. Could be other people, you know, as time goes on. You get down into really nitty-gritty issues with the way you implement things. And this little picture that I'm showing in the upper right is kind of showing that as the time-stamped symbol travels along the copper or the fiber. So, you know, in other words, as it's done exiting layer 1 or coming in layer 1, that's the point that the standard says you're time stamping at. But in reality, we all know, well, you're not actually time stamping precisely at that point. There's some point higher up in the PHY, or maybe even up at the MAC level, that's kind of symbolized by that red line there. That's where you're actually taking the timestamp with your hardware. Again, assuming hardware, but you're taking it up higher up in the hardware stack. And the question becomes, well, what's the difference in time from when I'm say I'm transmitting something? What's the difference in time between where I timestamp it, and then there's going to be some number of nanoseconds or picoseconds for it to get onto the copper or the fiber? And what is that difference? Well, the 2019 standard defined that as ingress-egress latency. And again, that's not latency from one product to another. That's just the red line to the blue line in that little figure. So what folks kind of discovered as they started implementing that and you know, getting really good accuracies out of it is that, well, if I've got an SFP module, there's some latency, you know, back and forth inside that module. And then there's other latency that's kind of outside the module, like inside my PHY implementation above the SFP. And so this amendment kind of breaks those into two separate parameters or pairs of parameters so that the SFP manufacturer can say, here's my transceiver latency for my SFP module. And believe it or not, there are SFP manufacturers that are starting to do this. And then the implementation above the module can have its own latencies. And those are kind of distinct because there's two different companies doing them, basically. Another aspect of this project is a mechanism to measure asymmetry on the medium. So you may remember I mentioned earlier that PTP just kind of assumes things are symmetric as they go one direction or the other direction. Well, for example, if you have different optical wavelengths, That's not true, at least not when you start getting down into picoseconds and so on. And there's a mechanism in this amendment to kind of measure that and account for it. And then, of course, there's management stuff for all of that. So some that were just recently started, as in the last couple of months or something. I'll kind of briefly touch on these. 1588H is kind of a funny one. It's an option to disable the announce message. So the announce message in PTP is required by 1588-2019, the current standard. And that's a message that's mostly used to decide where the grandmaster is, basically who's providing the source of time in the network. Well, inside a car or in many industrial applications, you essentially design your network with the grandmaster is here, and it's always here, and it's always in this box. I always know where it is. I never want to change it because it's just part of my network design. Therefore, I consider the announce message to be just wasteful stuff that I don't need. And so those industries formally asked 1588, can you provide a mechanism to make announce optional because we view that we don't need it? And so that actually was, after quite a bit of debate, was agreed to and is part of this amendment. So it'll provide an option to not use announce. 1588I was started just recently. That's a pretty simple one. If you have a product that supports multiple of these profiles that I mentioned earlier, so I support the automotive industry, I support telecom, so on and so forth. The question becomes, how do I configure that product to say, hey, I want to use the industrial profile? Well, believe it or not, there's nothing in the standard that did that for you. And so this amendment will add that to the MIB and Yang stuff, basically for management, so that you can do that and select which one you're using. And then 1588J, enhancements for unicast negotiation and performance monitoring. Those are two features that the telecom industry uses quite heavily. And there's, like anything else, they need some new features and some relatively small improvements to those things. And this was started a week or two ago and is going to basically cover that for the telecom folks. Another one that was relatively recently started, a little over a year, is P1588.1, which is probably interesting to this community. I'll kind of go over that. So in 1588-2019, there's a shall, basically a requirement that PTP messages are transmitted periodically, no matter what you are, no matter whether you consider yourself a client or a server, whatever it may be. And there's state machines for all of those messages and so on. So it can be kind of complicated. And there have been more than one open source project that tried to say, you know what, I don't need all of the state machines. I don't need all these periodic messages going at different rates and so on. What I really want is a client server model for unicast in particular, where I've got a grandmaster, a server that's giving me time. That thing just waits for a request from a client. And then and only then, so no periodic anything, it'll send a response back to that client and say, here you go, here's what you need for time. The simple PTP protocol that folks in Meta and OCP TAP kind of worked on, there's been past slides and presentations and so on in OCP TAP. That's one of the examples of a project that was really successful and kind of used this model. So basically, the working group kind of decided, yeah, we need this. We in general, not only data centers, but multiple industries need this sort of thing. Seems like a good idea. But actually trying to add that to the 1588 document itself would require some fairly fundamental changes and would add a bunch of if then else's to the big document. And the big document is already a big document. So the general kind of decision of the working group was, why don't we just put this simpler protocol in its own separate standard, its own separate document, where that protocol will be just documented as this is a simple client server protocol, and it's a standalone document. So that was the project that was started in May of last year. The idea being a new unicast protocol that uses the messages from 1588, but pretty much just kind of defines that simple client server model. And the idea, we had a recent meeting where we kind of agreed on this, that the goal is to use existing PTP cables, switches, and routers. So in other words, the new protocol will be on kind of either end, the client server end, but the network infrastructure in between, we want to use what's there now, and the thinking is that can be done and that can be accomplished. So the current status is there's been more discussion on kind of, well, who needs this and why and so on. And I think most of that has kind of been lumped into data centers and also some apps that would otherwise use NTP. NTP uses this very simple client server kind of model. And so for folks that are familiar with NTP but want the hardware timestamping capability, this is a good fit for them too, which may or may not be a data center. But there has been a lot of attraction of new members, which is a good thing. But it also generates a lot of new discussion. Why are we doing this? Why isn't 1588 good enough? And so on. Early on in the discussion, two of the major proposals were merged, SPTP and Flash PTP. Both of those were simple and were like one direction, one message each direction. And that was part of why those were merged. Other proposals have come along later. Not all of them have one message in each direction, which is, okay. But basically, there's been multiple alternative proposals since then. And so the idea, kind of the rough consensus so far, is that we're going to have a vote in early April to select one of those. Basically, not so much as this is the one and only thing, but at least to reach some agreement so that we can start making progress and moving into more detailed decisions. And so that's the state of that. So really briefly, I'll talk about some future things. So none of these have even been started, at least not officially yet, whereas all those ones I talked about before are kind of going on. So a few weeks ago, we had a February face-to-face meeting and discussed some new ideas for the future in that meeting. So I'm kind of summarizing it in the context of that. And so this is literally just a few weeks old. It's looking like there's going to be an amendment for security. The various things will probably go into that amendment, but I think the big one that would be noticed kind of outside the group would be TLS. So many of us know, HTTPS is secured with TLS. A lot of other protocols are secured with TLS. It's a very popular IP-based security mechanism from IETF. So there's going to be a project to basically do that and specify that for the 1588 authentication TLV. This is just personally kind of my prediction. I think for people that want to secure PTP and for whatever reason they don't like MACsec, one of the challenges that's been kind of ongoing with the 1588 TLV is, how do I do key management? How do I actually get this stuff to work? And the GDOI solution, I won't go into all the details, but it's a little bit specific to industrial and the power folks. Not everybody would want to use that, but everybody's very familiar with TLS, and IT folks that do security are very familiar with TLS. So more than likely for the folks that don't like MACsec, I have a feeling that once we get TLS in place with this amendment, that'll be the thing that people use to secure the authentication TLV. So it'll provide a really nice security option for folks that don't, for whatever reason, don't want to use MACsec and do want to do something for security for PTP. So this is a really good thing that's starting off. Another discussion we had was YY. YY is essentially a performance improvement for wireless time sync. So wireless time sync has been around for about a decade or so for, say, 802.11 but the YY proposal is an implementation that significantly improves performance. It's almost kind of like a white rabbit for wireless in a way. That's the way some folks have described it. It's great technology, and we discussed it in the meeting. my sense of it is that we've reached some consensus that, yeah, this is really great technology. The open question that remains is that it's more like an implementation right now. Like, here's how you would connect it to your clocks and so on. And the standard doesn't really get into here's this chip, here's that chip kinds of topics. So there's a lot of questions around, well, how would it fit into the 1588 document? What would it look like? And so the consensus that kind of came out of the meeting is that the promoters of YY will work on a presentation to just go into more, not answer every question, but go into more detail on like what is proposed for how it would be integrated into the standard. And that was a great discussion. Another thing that I kind of brought up was position. So again, we all kind of know that the wireless stuff is beginning to kind of ramp up for PTP, synchronizing different wireless products. The funny thing about wireless products compared to wired, like Ethernet and OTN, is wireless things move around. Drones, vehicles, robots, you name it. And time and position, or I don't know how to describe it, but technically intimate. In other words, when you measure time to synchronize, you measure the distance to your neighbors. When you measure position, you measure the distance to your neighbors to triangulate where your position is. So there's things that are kind of done for both in general. So it's reasonable for folks to kind of say, well, hey, maybe it makes sense to do both in one protocol. And that's been kind of just sort of generally coming up as a question. So for example, should position be added to PTP or for that matter to NTP? The YY protocol that I mentioned earlier has position in it and actually has information for doing that. I'm linking to a presentation that Mark Weiss did in TSAIW of OCP TAP, where his slides specifically asked this question for a protocol that the military, U.S. military, was using. Same kind of question, well, this other protocol needed to do position. Should it be integrated into PTP or NTP? The two big questions that came out of that discussion are similar to YY, how would it fit into 1588 or 1588.1? What would it look like? Not all the details, but just in general. And another concern here is, do we have the volunteers with position expertise? So folks in the room were kind of like, hey, we do timing. We all know timing in this room. We may or may not know position. Some of us have some experience, some don't. So do we have people that are willing to dedicate time to this and actually volunteer and state, yes, I know position synchronization or agreement really, really well. I know all the ins and outs, and I'm going to help you write text for it. If we don't have volunteers like that, at least my prediction would be it's not very likely to happen. So there would have to be some folks that would kind of step up and volunteer to take this sort of on. We did generally agree to have a presentation, hopefully by an expert in the next call. We could do a joint call with NTP. We have between 1588 and NTP, there's really great connections of people and stuff. And at the meeting, other proposals were discussed. So really quickly, I'll mention data centers. So timing in data centers. This is not, other than 1588.1, which is kind of related to data centers, this is sort of outside of the 1588 topic. So there's sort of two groups discussing timing in data centers now. I would say actually they're not really overlapping necessarily at the moment. So in ITU, in question 13, which is the synchronization group, there's a group working on a supplement, which is essentially, you could think of it as kind of a white paper. And that group is trying to produce a white paper. At least it's kind of become clear to me that that's kind of the goal of the group. And again, that's a totally reasonable goal. So for example, one of the topics that's coming up is what PTP protocols to put in that white paper. Some folks like the ITU profile, 8275.1. There is simple PTP, which is deployed in data centers, so on and so forth. That hasn't been decided yet, but but my kind of vague understanding is they're kind of working through the steps of like what goes in the supplement. And then of course there's the IEEE industry connection that I'm chairing, and is kind of held jointly with this group. Some of us have seen the joint meetings. I think where we are with that, and again, this is just my perception of it, is that we're trying to answer the question, assuming you have time sync and it's deployed and it's in a data center, how do you use it? And we could do a white paper in this industry connection group. I'm assuming we're going to defer the white paper until we have a pretty clear answer to that question. Part of the reason why I kind of showed the other applications is every other industry that has used PTP has answered that question first and then discussed things like, what PTP protocol do I use? What are the requirements and stuff? In other words, you decide why you're using it, and then you decide the requirements. So to me, I'm not too worried about the task of creating a white paper just for creating a white paper. I think the first thing is to kind of get more experience with actually using it. And I'm aware of some things that are going on behind the scenes where people are trying that and experimenting with different techniques and different reasons and so on and so forth. So I'm actually really optimistic at this point that we're going to get answers, to that question at some point. So I kind of feel like the industry connection can kind of be a little bit on idle until we start to get better information. And the ITU group will make great progress on their document. And so that is all I had.
I think, Rod, we already had 2 use cases. You are aware of them. One is congestion management, right, in data center.
Right.
And Matt presented the first part of it, and he will present the second one shortly. And the second one we discussed also is AI, or distributed machine learning.
Right.
It's what Dan has been discussing.
Right.
But you're right. We have to look for more. I agree.
Well, and I think, to be honest, those two are sufficient, maybe. I mean, as you've seen, like a lot of the other industries only have one, reason why they use something. So the fact that we have two that we're considering is already pretty good.
So maybe if you want, Rod, we can start drafting the white paper. It will be updated as we move along, right?
We could.
Yeah, like
No, for sure.
capture some of the stuff we discussed for congestion management and AI, and just as you know, for this kind of IC activities, the white paper keep it evolving. People add to it and discuss it.
Exactly. And I mean, you're right, Hesham, that maybe that is, and again, I don't mean to even criticize what ITU is doing. Maybe one way to make progress is to, like, here's a document. Do you agree with it? And if people disagree with the document, that's fine. You can make progress that way,
Exactly. Silvana is holding this meeting,
Yep.
the coordination meeting with ITU, your IC, and other consortiums, whatever. So, like what you said, Rod, we can go to them and tell them, here is the white paper. This is our current thinking. What do you think yourself?
Right. And I typically attend the actual Q13 meetings too. So I'm kind of following the progress of their document too, and so, yeah, I mean, you're right. It may be that ultimately the white papers are very similar. Yeah, I mean, if for no other reason than we have some of the same people working on them, and so, yeah.
I put in the chat that there's also databases, right? Pretty much all the major players use precise time to help with their databases, locking them and making sure their commits are proper.
Right.
So there are three applications.
That's one that already exists. I mean, in a way.
Yeah, exactly.
Yeah.
The other one, Rodney, to add to what Dan and Hesham already mentioned is while looking at congestion, one other additional topic that kind of touches in the other three, but I believe is a topic by itself, is diagnostic. So basically logging.
True.
So having the ability, especially at super high bandwidth, to timestamp packets and events at all nodes with some semblance of coherency will, like sifting through things where the link is 800 gig, the precision of 100 nanosecond is a lot of packets and a lot of transactions.
Right. And yeah, Med and I have been talking about that as well. And there's even some stuff going on in the diagnostics front. And Med is absolutely right that it seems like kind of a sort of low level thing, but getting an accurate time is very helpful for diagnosing problems when they occur.
Yeah, and you can add telemetry, in-band telemetry, or telemetry.
Well, in a way, I don't know, Med. In a way, I think that's what Med was referring to, right, Med?
Correct.
This telemetry.
Yeah, telemetry becomes a very potent tool once a coherent timing is added to it.
There is an IETF group working on in-band telemetry.
That is true.
Yeah.
Do you know, Hesham? Is it like an IETF working group, or is
No,
it
it is
within one of the
item.
other ones?
No, it is a work item in an IEEE working, an IETF working group. I can send you the information.
Yeah.
Yeah, I will send you the information.
I mean,
even have
maybe we should reach out to them at some point. And,
yeah. I have a draft actually. I have a draft about it for a different way of doing in-band telemetry. I will send you my draft too.
Huh. I mean, I'm just thinking out loud, but IETF has face-to-face meetings every now and then, and when they do, it's kind of okay to do sort of a presentation with,
Yes.
hey, here's an idea. Yeah, I mean,
exactly.
Maybe we could do something like that.
Yes, you can do that. Yes, you are. And the next meeting is in Bangalore, or Thailand. Yeah.
Oh, and in Bangkok, probably.
Yeah, Bangkok, you're right. So not Bangalore, it's India. Bangkok. Bangkok. I was in Bangkok many times before, but this time, I don't know. I don't like
that. you're like me. I don't know if I'm jumping for joy. I don't know, maybe.
I every time I go there, first time was exciting. After that, there's nothing.
Right.
So I will send you the information. The next meeting for IETF is in maybe a couple of weeks. It is 17th, I think, and you can attend remotely if you want.
No, you can. It might be a little late for us to get on their agenda. I know they tend to like to do their agendas way ahead of time.
Yes,
but
yes. Agenda is already finished. You're right.
Yeah.
Rodney,
Cool.
your great presentation. One question
thanks.
I was curious of that may touch on, I think, several of the things you mentioned. It's something I've considered for the financial services industry, which is we're now at the point where we're sometimes trying to get picosecond level timestamping. And the fundamental problem is, and this touches on the question of location you mentioned for YY, the GPS receivers just aren't good enough, especially the ones we tend to use in telco. So one of the things I've been considering trying to do is actually capture the raw GNS waveforms, inject them into Ethernet frames, and then you can record that in the same clock domain that you're tapping other fiber links, so that then later after the fact for post-processing, you can much more accurately then model what the exact time was. Because you start running into issues like atmospheric effects and other things that change it. And if you're trying to do that with a real-time device, it's not nearly as accurate as if you can see the full picture, and then you have other receiving stations whose data you can integrate in. Is that something that may make sense to put into like an IEEE protocol in the space? Or
that is a good question. I don't know. I mean, what it kind of reminds me of, and this is just me thinking out loud, is I don't know if you've seen the OCP TAP presentation recently that Julian did on kind of using SFPs to essentially get the GNSS signal, from the rooftop down.
Exactly.
Maybe it's related to that kind of idea, but I don't know, to be honest. It might be.
And then another one, I don't know again which organization this would be plugged into, but one of the problems you run into is that even the national labs aren't nearly as accurate as we need. So how do
That's
we
true.
actually get the values out of them? And then how do we reconcile them? So for
Right.
example, like you mentioned, like in finance, we're supposed to be comparing against NIST, but then we're actually using GNSS receivers that are tied to the USNO DoD standard from GPS. And then with
Right.
what accurate
Right.
are those reconciling? And then another one, but personally be extremely interested in, can we work on some way of getting official time when we're not relying on GPS? So we have these national labs. How should
Right.
we get NIST or whoever it is to every data center, at least in the United States, as precisely as possible? Because trying to do this over Wi-Fi, it's just not a good idea. I mean, we know how
Right.
to spoof these. It's not encrypted a lot of times. It's subject to jamming, and we have fiber. So what are we doing?
Right. So on that last one, I could try to get you plugged in ATIS, the kind of US equivalent of ITU. I guess that's maybe a description of what ATIS is. AT&T in particular has been raising that last question that you mentioned. Basically having more reliable ways to exchange, at least in the US, reliable ways to kind of mitigate GNSS problems and so on. And obviously AT&T in the US is a pretty big voice there, but they've been trying to raise visibility and get something started in ATIS for that.
I don't know.
So.
And then there was one other one you mentioned that triggered a question that I was especially interested in. It was the IEEE P1551588F. So one of the other issues we run into when we're trying to get very precise measurements is we need to know not only the latencies of the optics or the transceivers, but also the copper trace lengths on something like a switch or even a NIC. And this is a big problem in trading because some ports are just physically closer by up to sometimes tens of centimeters. And you have all these exchanges ripping their hair out trying to measure fiber optic cables. And I try to tell them, even if you get this down to the picometer, you're not doing it right.
Right, exactly. No, that's a really good point. And I mean, to be honest, and I guess you and I kind of know, right? There's a lot of folks in financial that are starting to look at White Rabbit. And I think a lot of it is because, well, they're working on the same sorts of problems, you know, ultimately.
Yeah, White Rabbit is pretty much treated as the gold standard. The problem I have with it, though, is it's still tied to GPS. And so it's like, okay, you picosecond time sync plus or minus 50 nanos. This doesn't make sense.
That is true.
And then you get into things like, what are the different types of oscillators? What is the stability? What are the error modes? What sort of standard deviations do you have on certainty? Things like that. And that was one other one I was curious about. So this sort of came out of sort of some of the thoughts for this another OCP-TAP subgroup. But has there ever been look at using multiple wavelengths so that you can measure the time of flight one way based on the fact that with different frequencies, they have, I think, a length-dependent component of this, how long it'll take them to transmit. So basically, you don't need to measure the ACK. You just get the right optics. And this used to maybe be cost prohibitive, but now it seems fairly cheap and growing.
Yeah, I was going to say, I think there are people in the White Rabbit community looking at that. To be honest, I don't know, but good idea. But I just don't know the answer.
In full disclosure, I sort of got the idea actually from GPS, so one of the new techniques they use.
Right, because that's what they do. That's true.
Exactly. That's how they do the ionospheric corrections, by using the difference between L1 and L5 if the frequency deltas are large enough. So it's like, well, if they're doing that, why can't we?
Yeah, exactly. I mean, I assume you kind of know, like, what the White Rabbit crowd typically does is they're using a single mode fiber.
Yep.
And so there's just one wavelength in each direction, and they simplify it that way, but you're right. You've got to do something a little more sophisticated as you go forward.
Yep.
But David, can we consider high frequency trading as a use case for using time synchronization in data center?
Yeah, so we use it extensively. We were some of the earliest adopters of PDP, of White Rabbit, many years before it was part of the system.
Yeah.
So here you go, Rod. You have four.
That's true. I didn't think of it, but that is another use case for data centers. So I guess in a way, I kind of just in the back of my mind took that one as a given, But you're right. That is another example.
Exactly. So we have congestion management. Matt is doing it. We have the AI with Dan. You have high frequency trading with David. and we have telemetry that also them mention, Matt mentioned. Come on, we have 4 use cases.
Yeah.
And another one that's popular, sort of similar to the finance aspect, is in cybersecurity. If you're trying to establish a causal chain of who hacked what when and what was the source, you need all the devices to agree very tightly. And especially as our packet rates go up, then our requirements are going to be tighter and tighter.
Yeah, that's a good one, actually. I like it.
Yeah. Yeah.
And
That's a really
another
good
one
one.
potentially is for if you're trying to do signal, again, going back almost to the position, if you're trying to do localization of transmitters, especially on the wireless side, then you have a series of receivers and you want to know as exactly as possible where are they, and then you want them as perfectly synced so then you can measure the deltas of when different nodes are seeing something. And so they use this again like on some of the wireless things like MIMO, and I could probably imagine some cute ways of combining that to have mesh networks that can even coordinate on when they transmit to do constructive interference or constructive building of the waveforms.
Cool. Well, I'm running over time. Anyone have any last kind of questions before we close?
Oh yeah, just for the one on the YY and the position.
Oh, yeah.
I assume they're going to use not just position, but also vector heading, velocity, acceleration, things like that.
Good question. I haven't looked. Where did that one go? I haven't looked at the YY stuff, or I haven't talked to Nobu and the folks on YY yet to know what they do. But
Okay.
if you look at those slides from the group that Mark worked with, they did have velocity and acceleration and things like that in their data. It's not it's just slides. Is all
Okay.
that I've seen. The guy that worked on that was potentially, I think, volunteering to get into more detail, you know, with it. And I think ultimately that's what it's going to take, right, to answer those questions. Is people are going to need to see more, you know, more detail about what the information is and how it's exchanged and so on. But I take it as a given that it's not just position; it's also velocity, acceleration, and a lot of other things, you know.
And I wouldn't be surprised if some of this gets into a problem of other engineers have solved this. It just may be classified.
Exactly.
You know? As you can probably tell from your photo with the drones, like, okay.
Exactly, especially for some things like that, maybe. But,
Rod, can we get the F1588F? I don't have a copy of this. 1588F, the latency stuff.
I can get you a copy of the
drafts. Thank you. That's good.
Yeah.
That'll be
so
good.
so to let you know, it's a little confusing right now in that it's in these parts. So they kind of split the work up into these two parts. So I can send you a draft of A and B. So they haven't merged them yet, but
that's good.
I could get you that. It's kind of inside the work group stuff, but you know, we can.
Thank you very much, Rod.
Yep. All right. Well, thanks everyone.
Bye-bye.
Just one last one since we have you. Another one that could be very useful is not just distributing time, but distributing actual clocks. So that if you didn't want to sync up a series of electronics and Ethernet that actually are all on the same clock domain, instead of having each one have their own local oscillator, that could then help with things like bit error rates and some other neat applications.
That's an interesting idea. Yeah.
It goes back to that problem of HFT. If you want everyone on the same clock domain, so you know, otherwise it's hard when you start running through dual clock FIFOs to then really know when exactly was it arrived in terms of in which clock domain are you been measuring it in.
Exactly. Well, and I mean, just thinking out loud, PTP has a concept of a clock domain. Basically, here's one domain of time and here's a different domain of time, and these are not synced.
Yep.
You know, they're running kind of independently. So there may be clever ways to communicate that sort of thing somehow. Yeah, actually, the industrial folks kind of already do that sort of thing. I'm getting into all the details, but yeah, no, that's a good idea.
I would think for some sort of mechanical for mechanical synchronizations, where it's less important exactly what time, but you really want things like, let's say, actuators that are distributed over a plane or a hypersonic missile. You want them operating at exactly the precise time.
Right. I mean, yeah, actually, you just happen to hit the nail on the head. Like the industrial folks will run two domains. One will be, you know, the domain that's connected to GNSS and, you know, and then another domain that's just, this is when the controller started, and I don't really care what date it is. Exactly. You know, And there's different reasons for having those be two separate things, you know. So yeah, I mean, you're right. That's what they do. But
Excellent. Oh, this was
Cool.
great. I really appreciate the presentation. So
Yeah,
thank you for
great,
your
great,
time.
thanks.
great presentation, Rod. Really, I liked it. Give good summary.
Awesome. Thanks.
Thank you very much. I have to go to my other meeting.
Yeah, I do too.
All right. So let's close then, and we'll see everyone in 2 weeks for a presentation by Will Creswick, unless something changes, with a title Implementation of a Chip Scale Atomic Clock. All right.
Cool.
Looking forward to it.
Awesome. Thanks, everyone.
Take
Thank
care,
you.
everyone.
Bye, everyone.